Hi! For this video, we'll be talking about circular motion. In physics, circular motion is the movement of an object along the circumference of a circle or a rotation along a circular path. It can be uniform with constant angular acceleration, or it can be non-uniform circular motion with a changing rate of rotation. So again, circular motion can either be uniform circular motion or non-uniform circular motion. When you have an object that is moving uniformly in a circular motion, then the rate of rotation has a constant speed. While for non-uniform motion or non-uniform circular motion, your object is spinning, either going faster or going slower. Now, in circular motion, these are the different quantities that are present. So let's take a look into them one by one. We have here angular displacement, or your change in your angular position. You have here your arc length, then you have your tangential velocity, you have your angular velocity, you have the radius, and then you have the acceleration. All of these will be discussed further in the next slides. So these quantities help us to describe the motion of an object moving in a circular path. So first, let's look into angular displacement and arc length. So what is angular displacement and what is arc length? Angular displacement is defined as the ratio of the arc length to the radius of curvature. Also, we can describe angular displacement as the change of position of an object moving along a circular path with respect to its position in the circle, which is expressed in radians or in degrees. So the SI unit for angular displacement can be radians or degrees. And radians is actually a unitless or a dimensionless unit, which is defined also as the ratio of, which is also a ratio between two lengths, which is your arc length and the radius. Now for your arc length is the distance traveled along a circular path. So if you have here an object that is moving along a circular path and it has moved from point A to point B, the distance of these two, if these 2 points is your arc length, and the ratio of that arc length and the radius from the center of the moving object in a circular path is your angular displacement. Expressing it in mathematical terms, your angular displacement is equal to your arc length divided by the radius. Or you can also express it as your arc length is equal to your angular displacement times the radius. Now your arc length can also be, or your arc length is, in one complete revolution, it's your circumference of the circle. So if an object completes one revolution, oops, just consider that as a perfect circle. But when an object covers an entire circle, so it completes one revolution. And that one revolution is the circumference of the circle. And a circumference is equal to, remember, circumference is equal to 2 pi r, or 2 times pi times radius of the circle. So meaning, if an object completes one revolution, then it's equal to the circumference of the circle, which is 2 pi radius. Thus, for one complete revolution, your angular displacement will be equal to, if your arc length is one complete revolution, then that becomes 2 pi r over r. You can cancel that out. Therefore, your angular displacement becomes 2 pi. That is if it completes one revolution. Okay? So this is the relationship between angular displacement and arc length. And Also, remember what I've said earlier, that radians is a dimensionless unit, because if you look into the formula for angular displacement, you have your angular displacement is equal to arc length over r. Your arc length is expressed in meters, while your radius is also expressed in meters. And meters divided by meter is, both of them cancels out. Both of them is canceled out. So you're left with no unit. But of course, we are describing a quantity here, so a unit is important. And this is actually considered as a unit, which is a ratio between two lengths. That's why this, instead of putting it as meter over meter, we express it as radians. So radians is the measure of angular displacement. And also, by the way, aside from expressing your angular displacement in radians, also you can express it in degrees. So in one complete revolution, that will be equal to, as we have mentioned in our earlier solutions here, that one revolution is equal to 2 pi radians. And it's also equal to 360 degrees. Remember that for one circle, it's equal to 360 degrees. Okay? So, of course, the unit here is radians. There. So that's angular displacement and arc length. Next, let's look into tangential velocity and angular velocity. So what's tangential velocity and what's angular velocity? Angular velocity, as you see in the illustration there, it's your angular velocity is the rate of change in angle, or the rate of change in angular displacement. So expressing your angular velocity in terms of angular displacement with respect to the changes in angular displacement with respect to time, then that will be angular velocity is equal to your angular displacement divided by the change in time that it took for it to change the position of an object with respect to the circular path, or with respect to its change in degrees. So the greater the angle of rotation, or the greater the angular displacement, of course, the greater the angular velocity. Now, your angular velocity is expressed since your angular displacement is expressed in radians, then your change in time is expressed in seconds. Therefore, your angular velocity is expressed in radians per second. Now, for your tangential velocity is the velocity of an object that is analogous to, or that is also the linear speed of an object that is moving along a circular path. If the object is not moving along a circular path, then it will move in a straight line and it will have the velocity with the same magnitude of your tangential velocity. So your tangential velocity is your rate of change in the distance divided by, or the rate of change in position in linear, or which is your arc length, divided by, of course, the time it took for the change, or the time it took for the object to cover that change in position. So therefore, your tangential velocity, or sometimes it's just called velocity, is equal to your arc length divided by time, or change in time. And your unit for tangential velocity is, of course, meters per second. Now, looking into the relationship between tangential velocity and angular velocity, so we can actually express them or we can actually relate angular velocity and tangential velocity. Remember that your angular displacement is equal to your arc length divided by your radius. Okay? If your arc length is equal to or if your angular displacement is equal to arc length divided by your radius, then we can express this, or we can change this expression to this one. So therefore, let me just erase this one. Oops. There. Therefore, your angular velocity becomes, if your angular displacement is equal to arc length divided by radius, so that becomes arc length divided by change in time times radius. And what is arc length divided by change in time? That is your tangential velocity. Therefore, your angular velocity is equal to tangential velocity over r, which can be also expressed as tangential velocity is equal to your angular velocity times r. If we are going to look into the relationship between tangential velocity and angular velocity. Next, let us describe the relationship between angular velocity and tangential velocity using a moving car. When a car moves, of course, it moves because the tires are rotating. And a rotating tire is, of course, an example of a circular motion or an object that's moving in circles. The speed by which your car moves is dependent on how fast your tires are rotating. So if we take this equation, you have your tangential velocity is equal to your radius multiplied by the angular velocity. Your tangential velocity will actually be the speed by which the car also moves. Because again, your tangential velocity is also your linear velocity if your object is not moving in a circular path. So let's establish that. The tangential velocity of the tires will be your velocity, will be the velocity as well of the car. So if we have this mathematical equation, we know that if we increase the radius of the tires, you will have bigger velocity. Therefore, for bigger tires, you'll have faster speeds or faster velocities. And of course, the faster the tires are spinning, then you will have greater value for velocity as well, or the car will also move faster. Next, let's describe acceleration. Now, in circular motion, there are quite a number of accelerations that are present. Of course, for a recap, acceleration is the rate of change of velocity. Either there's a change in magnitude, there's a change in direction, or there's a change in both magnitude and direction. Now, the acceleration of an object moving along a circular path is or can be resolved into two components. That will be tangential acceleration and centripetal or radial acceleration. So let's take this one for example. If we have here an object moving along this path, let me rewrite that circle. If you have an object moving along this circular path, so let's just imagine that's a perfect circle. So if you have that object, then taking this position, for example, there are two components of the acceleration. You have your tangential acceleration and the radial acceleration. What's the tangential acceleration? Tangential acceleration is the component of the acceleration that is, of course, by the term itself, tangential to the path of the circle. While your centripetal acceleration or radial acceleration is the acceleration that points or directed towards the center of the circle. Now, what does these two acceleration do? Remember that when there's acceleration, there's a change, either in magnitude or either in the direction or either both magnitude and direction. Tangential velocity will be the one responsible for affecting the speed of the, or it will be the one responsible for increasing or decreasing the speed of the rotating body. While for your Centripetal or radial acceleration, it will be the one responsible for any changes in direction. Remember that tangential velocity always changes its direction. Because if you have an object that is moving in a circular path, so if the object is at that position, then it will have that tangential velocity. If the object is now here, then it will have that tangential velocity. So your object that is moving along a circular path, even though it's in uniform motion, where we say na it doesn't change its speed, but it changes its direction. That's why it's still accelerated. So going into the components of this acceleration, again, your tangential acceleration is the acceleration that is in tangent to the circular path, and your centripetal acceleration is your acceleration that is directed towards the center of the circle. And your tangential and centripetal acceleration are perpendicular to each other. That's why to solve for the acceleration of our object moving along a circular path, we can use the Pythagorean theorem. So we just take the sum of squares of the tangential acceleration and centripetal acceleration and take the square root. Now, how do we solve for tangential acceleration? So tangential acceleration as presented here is equal to this is angular acceleration times the radius. And what is angular acceleration? Angular acceleration is of course, rate of change in angular velocity. So if that's the case, then we can express angular acceleration that is represented by alpha. So you have angular acceleration is equal to change in angular velocity over, of course, time. If that's the case, then therefore your tangential acceleration can also be equal to your change in angular velocity divided by time times. So that's your tangential acceleration. Also, since your change in um, angular acceleration divided by your change in time is your angular acceleration, then oops, you have this equation. So both of them are equal since you just use this to derive another equation using your angular velocity and using the time. So again, tangential acceleration. Also, tangential acceleration can either be parallel or anti-parallel to your tangential velocity. So when you say parallel or anti-parallel, if you have here a circle, or if you have here an object moving along a circle, if that is your tangential velocity, so your tangential acceleration can be parallel to that, or it can be anti-parallel. So if the tangential acceleration is parallel to your tangential velocity, then your object moving along circular path will be speeding up. While if the tangential acceleration is anti-parallel, then your object will be slowing down. Now let's look into centripetal or radial acceleration. So centripetal or radial acceleration actually keeps the body to move in a circular path. And your centripetal acceleration is caused by a force, because remember, acceleration is present when there's a net force. And that force is centripetal force, which we will discuss a bit more later after this slide. So your centripetal or radial acceleration is mathematically expressed as here you have a sub r, or radial acceleration, is equal to your tangential velocity squared divided by r, and you have also it can be expressed as your angular velocity squared multiplied by r. So if you know both the tangential acceleration and centripetal acceleration, then you can solve for the acceleration of the object moving along a circular path. And your object that is moving along a circular path is, of course, it is always accelerated, which means it always changes its velocity, either a change in direction or a change in the magnitude. Now, in uniform circular motion, take note of this. In uniform circular motion, tangential acceleration is not present or is non-existent. Because in uniform circular motion, your tangential velocity only changes its direction. And the change in direction in tangential velocity is attributed to the presence of centripetal acceleration. But of course, for non-uniform circular motion, if the object is speeding up or slowing down, then tangential acceleration will be present. So for uniform circular motion, only centripetal or radial acceleration is present. So again, you have tangential acceleration, centripetal or radial acceleration, and you also have angular acceleration. Centripetal and tangential acceleration are components of the acceleration of your moving object in a circular path. So as I mentioned, since the object is accelerating, there must be a force to keep it moving in a circle. If you imagine, if you have an object that's moving along a line, it will turn or it will make a curve and continue to move along a circle if something pulls it towards a fixed point. And that force is called as your centripetal force. Now, if you remember in your previous lesson in high school, that force is equal to mass times acceleration. And we have learned earlier that acceleration is your centripetal acceleration, which is the one that is caused by your centripetal force, is equal to v squared over r, or also equal to omega squared times r. So if force is equal to mass times acceleration, then therefore your centripetal force will be equal to mass times your tangential velocity squared divided by r, or equal to mass times your angular velocity squared times r, where mass of course is kilogram. Therefore, since it's force, then the SI unit, or the unit which we express centripetal force, is Newton, or of course kilogram meter per second squared. So now let's do some sample problems. A car that has tires with radius 20.0 centimeters begin to accelerate forward. The acceleration comes from the engine, which produces an angular acceleration of the tires at 12 radians per second squared. So this is squared. What is the tangential acceleration of the tires? So what are our given values? We are given the radius, which is 20.0 centimeters. And then we are given your angular acceleration, which is 12.0 radians per second squared. And we are asked to solve for the tangential acceleration. Now, what we need to do here first is we need to convert this one into meters. So how do you convert centimeters to meters? 20 centimeters times the conversion factor will be 1 meter is equal to 100 centimeters. So that gets cancelled, and we're left with 0.2 meters. Now we have angular velocity, angular acceleration, and radius, and we can use both of these values to solve for tangential acceleration. Because tangential acceleration can be calculated using angular acceleration multiplied by the radius. So if that's the case, then you just put 12 radians per second times 0.2 meters. So what will be our answer there? So let's open our calculators. So that becomes 12.0 times 0.2. That is 2.4. What will be the unit? So it will be meters per second squared. So this is now your tangential acceleration. Again, radians is a ratio of length. So radians is also meter over meter. So if you multiply radians by meter, then you get meter. Okay, take note of that. Next, a ball at the end of a string is swinging in a horizontal circle radius of 1.15 meters. The ball makes exactly 2 revolutions per second. What's the centripetal acceleration? So we are asked about the centripetal acceleration or the radial acceleration, right? And the given values are the radius, which is 1.5 meters, and we are given 2 revolutions per second. And what is this? This is actually your angular velocity. You have 2 revolutions per second. Now, we need to convert here your angular velocity to be expressed in radians per second so that we can use that value and operate it with your radius, which is expressed in meters. So your angular velocity is 2.0 revolutions per second Converting that, we know that 1 revolution is equal to 2 pi radians. There. Therefore, the angular velocity of our object expressed in radians per second is 2 times 2 pi. So that gives us 4 pi radians per second. That's our angular velocity. Now, how do we solve for your centripetal acceleration? Remember that your centripetal acceleration or radial acceleration can be solved using your angular velocity squared multiplied by the radius. So substituting your values, you have 4 pi radians per second squared times 1.15 meters. And that will be 4 pi times 1.15. You have 4 pi squared. Do not forget to square both 4 and pi, or pi squared, multiplied by 1.15. So that is equal to 181 or approximately 181.6. The unit will be meters per second squared. Because radians squared is still dimensionless, divided by second squared, that's second squared. So you multiply radians squared by meter, that's still meter. So your radial acceleration or centripetal acceleration is approximately 181.6 meters per second squared. Calculate the angular velocity of a zero of a 0.3 meter radius car tire when a car travels at 15 meters per second squared. So what is asked from here? We are asked of the angular velocity. And we are given the radius of the car tire, which is 0.300 meters. And we are given with the velocity of the car, which is 15.0 meters per second. So if you remember, with our analogy earlier with angular acceleration and with angular velocity and tangential velocity in a moving car, we know that the car or the speed of the car is also the tangential velocity of the tires. So therefore, we can use this speed of car as the tangential velocity. And what's a formula to solve for angular velocity? Angular velocity is just your tangential velocity over the radius. Your angular velocity is equal to 15.0 meters per second divided by 0.300 meters. If that's our equation, then 15.0 divided by 0.300. Then we get angular velocity will be 50, your unit is radians per second. This is now a ratio of two lengths, which is expressed in radians since we are talking about circular motion. And then another example, an automobile with 0.260 meter radius tires travels 80,000 kilometers before wearing them out. An automobile can travel 80,000 kilometers before it gets wear out. How many revolutions do the tires make, neglecting any backing up and any change in radius due to wear? So at how many rotations can it make if we don't factor in backing up in the change in radius because of the wear and tear of the car, of the tire? So you're asked about how many revolutions. And we are given radius, which is 0.260 meters. And we are given a distance of 80,000 kilometers. Remember that your distance here, it says here that the tire can travel 80,000 kilometers. And that is also your arc length. So if that is your arc length, and this is your radius, this 0.260 meters, you can actually solve for the angular displacement, where angular displacement is equal to your arc length divided by the radius. So substituting your values, that is 80,000 kilometers divided by 0.260 meters. And of course, you cannot immediately proceed because you need to convert kilometers into meters. So converting kilometers into meters, then you'll get 1 kilometer is equal to 1,000 meters. So everything gets cancelled and you're left with no unit for length, and that is radians. So that's 80,000 kilometers divided by 0.260 times 1,000. So we have approximately 307,692,307.69 radians. Now, we can actually skip this one out, right? Because we are trying to solve for how many revolutions will the car take. Now, what's the relationship between or what's the conversion factor between radians and your revolutions? So you know that 2 pi radians is 1 revolution. And if this is unitless already, then radians can also be cancelled out. Because remember, the output here, or the result here, will be radians. So you're left with revolutions. So therefore, our answer here, in revolutions, you have 80,000 divided by 0.260 times the conversion factor 1,000 meters divided by 1 kilometer times 1 rev divided by 2 pi. We get approximately, our answer is approximately, so we have 48970,751.72 revolutions, or expressing it in much simpler expression, then we can have it as 5 times 10 raised to 7 revolutions or rotations. You have 1, 2, 3, 4, 5, 6, 7. So that's 5 times 10 raised to 7 revolutions. Therefore, before the tires becomes before the tires become unusable because of wear and tear, then it can rotate 5 times 10 raised to 7 revolutions, approximately 5 times 10 raised to 7 revolutions. So that's it for our lesson on circular motion. Basically, circular motion involves an object that is moving along a circular path, and the quantities that is present and the quantities that we can use in describing the motion of an object moving along a circular path is your arc length, you have your angular displacement, you have your angular velocity, you have your tangential velocity, and then you have your angular acceleration, and you have acceleration, which can be resolved into tangential acceleration and centripetal acceleration. And the one that causes centripetal acceleration is your centripetal force. So thank you very much for listening, and see you in the next video. Bye.